more than 23 million tons. That is the amount of copper mined worldwide each year to support power systems, transportation, and nearly all of modern industry. But producing that much metal requires a large-scale and highly energy-intensive production chain. Copper ore is crushed and separated from waste rock through flotation, then smelted at high temperatures and electrolytically refined to a purity of 99.99%. Finally, the copper is melted, continuously cast, rolled, and coiled into raw material for electrical wires, power cables, motors, and countless modern devices. In today's video, join Factron Process as we explore how humans transform seemingly worthless rocks into one of the most important metals in the modern world. With a history spanning more than 10,000 years, copper was one of the first metals to accompany human civilization. From the early Bronze Age to today's era of electrification, this material has remained irreplaceable because of its high durability and exceptional electrical and thermal conductivity. From electrical wires hidden behind walls and power outlets inside homes, to phones, computers, and transmission lines outside cities, copper quietly appears in nearly everything that keeps modern life running each day. This essential role has turned copper into a massive metal market, estimated at $269 billion annually. In particular, copper can be recycled almost 100% without any loss of quality. In fact, around 80% of all copper ever mined throughout human history remains in circulation and continues to serve the economy. After more than 10 millennia, copper has never become obsolete and remains the lifeblood supporting the development of the future world. Copper rarely occurs underground as pure metal that can be mined directly. Most of it is contained within minerals dispersed through millions of tons of rock, sometimes at grades of only around 1% or less. Therefore, before the first blast takes place, mining companies must conduct years of exploration to determine the location, size, and economic value of the ore body. The process begins with geological surveys covering tens to hundreds of square kilometers. Geologists study rock formations, collect samples, and search for signs of copper-bearing minerals. Once a promising area is identified, exploration drilling rigs drill into the ground to extract cylindrical rock cores. Each drill hole may extend from several hundred meters to more than 1 kilometer. The recovered cores are marked, photographed, and sent to laboratories for mineral and copper-grade analysis. Using hundreds of drill samples, engineers determine which sections contain valuable ore and which consist of uneconomic rock. All of the data is used to create a 3D model showing the shape, depth, and copper-grade distribution of the ore body. Specialists also calculate the amount of recoverable metal and the costs of stripping, grinding, transportation, energy, and waste treatment to evaluate the project's economic viability. Once the deposit is confirmed to be mineable, the overlying soil and rock are removed, haul roads are constructed, and mining benches begin to form along the pit walls, creating a massive open-pit mine. Across each bench, large drilling rigs drill hundreds of blast holes according to patterns designed by engineers. Each hole is typically around 250 millimeters in diameter and 10 to 20 meters deep. The spacing and explosive charge are calculated according to rock hardness and the fragment size that the crushing system can handle. The holes are then loaded with industrial explosives, most commonly ANFO, while the upper sections are filled with inert material to contain the explosive energy. When the electronic detonator system is activated, the holes explode with delays of only a few thousandths of a second, helping control rock fragmentation, reduce vibration, and limit oversized rocks. In only a few seconds, part of the mine wall is broken into thousands of smaller fragments. Once the area is declared safe, enormous hydraulic excavators and electric rope shovels begin loading buckets of material weighing tens of tons into waiting haul trucks. Based on the 3D ore body model and grade control data, the dispatch system determines which trucks deliver ore to the processing plant, which carry low-grade ore to stockpiles, and which transport uneconomic rock to waste disposal areas. Dozens of trucks continuously travel along winding haul roads day and night, maintaining a stable supply of ore for the processing plant. But removing the ore from the ground is only the beginning. To recover the copper, these rocks must first be crushed into much smaller pieces. Each truck unloads its ore into a primary crusher, where rocks nearly 1 meter in size are quickly reduced before continuing into the mineral processing plant. Here, the ore enters a SAG mill, one of the largest machines in the entire processing line. As the steel drum continuously rotates, hundreds of tons of ore and steel balls are repeatedly lifted and dropped, creating powerful impacts that break apart the layers of rock surrounding the copper minerals. The ore then passes through a ball mill for finer grinding until the particles measure only around 150 micrometers. At this point, the copper mineral particles are finally released from the rock that has trapped them for millions of years. Interestingly, grinding often consumes up to 60% of the electricity used by the entire mineral processing plant. In mining, the greatest challenge is not finding copper, but separating the extremely small mineral particles locked inside rock for millions of years. After several hours of continuous grinding, the ore has become a fine slurry. However, the copper has still not been separated. The copper mineral particles remain mixed with countless rock particles of nearly identical size, making separation with ordinary screens or filters almost impossible. To solve this problem, the plant uses flotation, a method that relies on tiny air bubbles to separate copper minerals from rock. First, the ore slurry is transferred into flotation cells, where a small amount of flotation reagent is added. This chemical does not dissolve the copper. Instead, it coats the surfaces of the copper mineral particles, making them less likely to attract water than ordinary rock particles. As air is continuously injected from the bottom of the cells, millions of tiny bubbles quickly form. The copper mineral particles coated with reagent attach themselves to these bubbles and gradually rise to the surface, while most of the waste rock remains below. Through this mechanism, ore containing only around 1% copper can be upgraded into copper concentrate containing approximately 25% to 35% copper, making it suitable for the smelting stage. After being separated from the original ore slurry, the copper concentrate is transported into enormous smelting furnaces. This stage uses extremely high temperatures to remove the remaining impurities and recover copper metal. A conveyor system continuously feeds the concentrate into the furnaces, where temperatures are maintained at around 2,300 degrees Fahrenheit, 1,260 degrees Celsius. Under this intense heat, the concentrate gradually melts, while impurities such as iron begin separating from the copper and rise to the surface as a layer of slag. Workers continuously monitor the inside of the furnace and operate specialized equipment to remove this slag, allowing the molten copper underneath to become increasingly pure. Once smelting is complete, the furnace tap is opened, allowing the molten copper to flow through channels into the casting system. Here, the copper is poured into large molds and solidifies into crude copper plates with a purity of approximately 99%. For the first time in the entire journey, copper no longer exists as a mineral mixed inside rock, but has become metal plates ready for the next refining stage. After being cast into plates, the copper is lifted and transported to the electrolysis area for the final refining stage. Here, each copper plate is suspended inside enormous electrolytic tanks, alternating with thin metal sheets. When direct current is supplied to the system, copper from the crude copper plates begins to separate, dissolve into the solution, and gradually deposit onto the neighboring metal sheets. This process continues for around 7 to 10 days. Each day, the new copper layer grows thicker, while most impurities do not follow the copper and instead settle at the bottom of the tanks for separate recovery. Once the required thickness has been reached, the new copper sheets are lifted from the tanks, washed, inspected, and transferred to the forming stage. At this point, the copper has reached a purity of up to 99.99%, making it suitable for use in the production of electrical cables, motors, transformers, and thousands of other electrical devices. After leaving the electrolysis area, the pure copper cathode sheets still do not have the appropriate shape for producing electrical wire, power cables, or motor windings. They are therefore transferred into a continuous forming line, where the copper undergoes melting, casting, rolling, and final coiling. Cathode sheets are loaded into a furnace operating at more than 2,000 degrees Fahrenheit, equivalent to over 1,093 degrees Celsius. Under the intense heat, the copper gradually melts and combines into a uniform stream of orange-red molten metal. Its temperature, composition, and oxygen content are closely controlled to maintain the metal's purity and electrical conductivity. Once it reaches a stable condition, the molten copper flows through heat-resistant channels into the continuous casting system. Here, the liquid metal enters a carefully cooled mold and quickly solidifies into one long, continuous copper bar. Instead of being cut into separate sections, the still-hot copper bar moves directly into the rolling system behind the caster. It passes through a series of rolling stands, where pairs of rollers continuously reduce its cross-sectional area. With each rolling pass, the copper bar becomes smaller, longer, and gradually reaches the required uniform diameter. After leaving the rolling stands, the material passes through cleaning and cooling systems to remove the oxide layer, stabilize its temperature, and protect its surface. The copper rod is then guided into an automatic coiling machine, where it is bent into uniform loops and arranged into large coils. Once the required weight has been reached, the copper rod is cut, strapped, inspected, and marked with an identification code. An overhead crane lifts each coil, weighing several tons, into storage, ready to be transported to wire drawing plants for the production of electrical wire, power cables, and many other copper products. Alongside mining, an important share of the global copper supply comes from products that have reached the end of their useful life. In 2023, secondary refined copper production reached approximately 4.5 million tons, nearly 20% of total global output. In other words, almost 1 out of every 5 tons of refined copper comes from recycling. The process begins with collecting old wires, motors, transformers, copper pipes, and circuit boards from demolition sites, repair workshops, scrap yards, and electronic waste centers. Because many types of scrap contain far more copper than natural ore with grades below 1%, they're considered a form of urban copper mine. At the plant, the scrap is sorted to remove plastic, rubber, wood, and fabric. Magnets separate iron, while XRF scanners identify metal composition within 2 to 5 seconds. A modern line can process between 20 and 50 tons of scrap per hour. Electrical wires and cables pass through stripping machines before the copper cores are cut and reduced to particles measuring approximately 3 to 8 millimeters. Screens, airflow systems, and gravity tables then remove plastic, iron, and lighter materials, producing copper granules with a purity of 99% or higher. After dust, grease, paint, and oxide layers are removed, the scrap enters a furnace operating above 1,085 degrees Celsius. The copper melts into orange-red liquid metal, while flux combines with impurities to form removable slag. Finally, the molten copper is cast into ingots, bars, or sheets, or sent through a continuous casting line before being rolled, drawn into wire, and manufactured into new products. Compared with production from ore, copper recycling can save up to 85% of the energy, approximately 100 million megawatt-hours of electricity, and nearly 40 million tons of carbon dioxide each year. For millions of years, copper existed only as tiny mineral particles locked inside rock. Without modern technology, these particles would be almost impossible to separate and use. Only after passing through exploration, drilling and blasting, ore grinding, flotation, smelting, electrolysis, and precise forming processes does copper become coils of metal with a purity of up to 99.99%. From there, this red metal is drawn into wire and manufactured into power cables, motor windings, transformers, and thousands of other components. Copper lies behind walls, inside vehicles, factories, power grids, computers, and nearly every electronic device we use each day. We rarely see copper at work, yet it quietly carries electricity, transfers heat and keeps countless machines running. Every light that turns on, every motor that begins to rotate, and every device that connects depends in some way on this metal. Even when electrical wires, motors, or electronic devices reach the end of their useful lives, the copper inside can still be recovered, cleaned, melted, and returned to the production line in a new form. Perhaps that is copper's most remarkable value. It is not as brilliant as gold or as visible as steel, yet it is almost impossible to replace. From rocks hidden deep inside mountains to metal carrying energy across entire cities, copper continues to quietly support the modern world. To continue exploring how ordinary raw materials are transformed into the products that keep the world running, subscribe to Factron Process. Thank you for watching, and we will see you in the next video.